presentation. My name is Peng. I'm an assistant professor in Singapore University of Technology and Design. Together with Ziqi Wang from Swiss Federal Institute of Technology, Zurich, Switzerland, and Michael Livesu from Institute of Applied Mathematics and Information Technologies, CNR, Italy, we will present a tutorial on computational assemblies, analysis, design, and fabrication. Here are the three presenters of this tutorial. In this tutorial, we will introduce computational techniques to analyze, design, and fabricate assemblies, an emerging research area named computational assemblies. We will review and categorize recent research works on computational assemblies, focusing on representations, methods, and algorithms. We will also provide insight of challenges in the research area and point out future research directions. This tutorial is aimed at two classes of audiences. The first class is students and researchers who are looking for an entry point into this exciting area. The second class is designers and makers who are interested in making use of computational tools to create assembly designs. Here is a rough timetable of this tutorial. I will start with an introduction and then present computational methods for analyzing different aspects of given assemblies. Next, Ziqi will present computational methods for designing assemblies for usage in different applications. And Michael will introduce computational methods for fabricating complex shapes as assemblies. Lastly, we will have some time to take questions from the audience. So let me get started on the introduction. Assemblies are ubiquitous in our daily life, such as a chair shown here. An assembly has a specific form and functionality. For example, the functionality of the chair is that people can sit on it. To this end, the chair has to be structurally stable under external forces. An assembly is composed of multiple parts that are connected by joints. In this chair example, each part has an elongated or planar shape. And the parts are connected by joints integrated on the parts, aiming to make the chair stable. In this tutorial, we are looking at assembled objects instead of monolithic objects shown on the left, which are just cut out from a single block of material. This type of assemblies comes with a number of advantages. First, assemblies can help us to simplify the fabrication process. We can simply fabricate geometrically much simpler parts and then assemble them into a compound object, which can have a much more complicated shape and also interesting functionality. The second advantage is to store and transport the component parts in a compact way. This is the reason that when we purchase a piece of furniture from Archive, we usually receive a package of furniture parts that are compactly packed in a box. Third, we can easily maintain an assembled structure. For example, we can replace a broken part instead of remaking a whole structure. Assemblies can have multiple forms. They can be reconfigured in various ways, which incidentally allows multiple functionalities. People design assemblies for using them in different applications. For example, toy assemblies for entertainment, electronic devices for communication, furniture and architecture for resting and living, respectively. In this scenario, people are more interested in the functionality of assemblies. People may also focus on the form of assemblies. This typically happens when making complex 3D shapes with digital fabrication. For example, laser cutting is a widely used digital fabrication technique. One limitation of laser cutting is that they can only fabricate 2D shapes. Then, how can we fabricate a 3D bunny using a 2D laser cutting? The solution is to represent a 3D bunny as an assembly with planar parts. Then, we fabricate each planar part using 2D laser cutting and assemble these planar parts into a final 3D object. By using this assembly-based fabrication method, we can have a 3D laser cut bunny as shown on the right. Traditionally, designing assemblies is a challenging task, restricted to the professionals, since it requires extensive knowledge in geometry modeling, structural analysis, and rapid prototyping. Here is a diagram that shows the traditional design process. One first draws some sketches about the assembly, and then do some planning and modeling to design component parts and their connection. Next, he or she does fast prototyping to evaluate the assembly's performance. In case the performance is not desirable, he or she may need to investigate the reason. If it is because of large fabrication errors, he or she needs to redo the prototyping. If it is because of bad designs, he or she needs to redo the planning and the modeling process. To obtain a desirable mechanism, many iterations among design, prototype, and evaluation need to be performed, which can be very costly. To overcome the limitation of a traditional design process, currently there is a trend to study and develop computational techniques for analyzing, designing, and fabricating assemblies. We name this emerging research area computational assemblies. Users simply specify some high-level inputs or requirements on the assemblies, such as the number of parts, global appearance, structural performance, and so on. Then researchers can analyze the design problem and develop a specific computational algorithm or tool to automatically generate assembly designs, possibly with some user control or intervention. The generated assembly design contains all the information that are necessary for digital fabrication, including parts geometry, joint geometry, assembly plan, and so on. A final production can be obtained by sending the design to a digital fabrication device. This computational design method has two advantages. First, it enables general users to design personalized assemblies, since they only need to focus on the high-level specifications of assemblies, while algorithms take over the low-level computations. Second, it enables to generate assembly designs with optimized performance. This is because algorithms can explore the huge design space much more efficiently than human beings. Here we show an example. One wants to fabricate a 3D hand shape with laser cutting. Moreover, he or she wants to arrange laser cut slices according to a smooth cross field defined over the hand surface. To address this specific design problem, an approach called field-aligned mesh geometry has been developed to automatically generate the shape of each planar part for laser cutting, as well as the assembly plane for physical construction. The resulting laser cut hand assembly is shown on the right. Computational assemblies is an emerging research area strongly motivated by the recent advances in digital fabrication. Many aspects of assemblies can be studied and researched in this area. The first aspect is part fabricability. We know that each digital fabrication has its own strengths and limitations. Representing a given 3D shape as an assembly with fabricable parts is one possible way to accommodate these limitations. For example, we can decompose a complex 3D shape into a set of parts that can be fabricated by 3-axis Cnc milling shown here. Or we can save the total fabrication cost and time by combining complementary strengths of multiple digital fabrication techniques, such as laser cutting and 3D printing. Part joining is another important aspect in computational assemblies. To encourage disassembly and reuse of the parts, reversible joining methods are preferred for connecting the parts. For example, we can make use of 3D printable external joints to connect beams to make a structurally stable beam assembly. Or we can design decorative joints not only for connecting the parts, but also for making the assembly visually appealing. Fabricated parts have to be assembled to form the final object. However, finding the assembly sequence and the motion can be a challenging task. To address this challenge, computational methods can be developed to search for an assembly sequence that can minimize the scaffold required to assemble an architectural structure. Other research works may focus on the assembly motion. For example, compute non-trivial assembly motions to solve a two-piece disentanglement puzzle. In general, an assembly has to be structurally stable for practical usage. One interesting research problem is to design structurally stable assemblies with reversible joints, such as self-supporting structures with planar contacts shown here. Such assemblies can be in equilibrium after a specific external force, such as gravity. They can also be interlocking to bear external forces from arbitrary directions. Assembly aesthetics care about the appearance of the assembly object. In 3D printing, cutting things on a 3D printed assembly can hurt its aesthetics. Hence, computational methods can be developed to put these cutting things at unnoticeable regions of an object, aiming to make them less distracting. To fabricate a 3D shape with multiple colors or materials, one possible way is to decompose it into multiple parts and assign a single color or material to each individual part, as shown in this example. Reconfigurable assemblies consist of a common set of parts that can be rearranged into multiple forms for use in different situations. In these assemblies, the component parts can be free for reconfiguration, meaning that each part can perform 6 degrees of freedom motion when transforming from one configuration to another configuration. Alternatively, the parts can be always hinged during the reconfiguration, such as the transformer shown here. Component parts can be reused to increase their utilization. In this architectural surface example, if many parts have exactly the same shape, then they can be fabricated by using the same mold. In other words, the mold can be reused for fabricating many parts. Designing reusable parts can be formulated as a top-down problem, where the assembly shape is given and the goal is to design a small set of discrete equivalence classes of the parts. Sometimes reusable parts are given and fixed, such as Lego bricks. using their instances to approximate a given shape can be formulated as a bottom-up problem to look for an optimal layout of the parts. Designing assemblies for functionalities is also an interesting research problem. For example, designing furniture assemblies for bearing external forces, and designing 3D printable assemblies with electronic components for user interaction. In this topic, analyzing and measuring a specific functionality is an essential yet challenging task. One core problem in these research works is computational analysis of various aspects of assemblies, which will be necessary not only for evaluating generated designs automatically, but also for guiding the assembly design process. Taking the analysis method as a foundation, various computational methods can be proposed for designing assemblies that can be used in different situations, focusing on their functionality. Alternatively, we can also focus on the form of an assembly instead of its functionality. This typically happens when we propose computational methods to represent complex 3D shapes as assemblies for digital fabrication. To define the scope of this tutorial a bit further, we are focusing on structures as opposed to mechanisms. As you can see the video on the right, the core functionality of mechanisms is a motion generated by the assembly. Our focus is structures that remain static. Once all the parts are put together, here we do a bit more comparison between structures and the mechanisms. Structures are mainly used for transferring forces, while mechanisms can transfer both motion and force. Structures are widely used in furniture, architecture, and puzzles, while mechanisms can be found in machines, robots, and mechanical toys. Typical parts in structures have elongated, planar, or solid shapes, while typical parts in mechanisms are gears, linkages, and cams. When designing structures, we focus on their structural stability under external forces. In contrast, when designing mechanisms, we focus on the mechanism's kinematic and dynamic performance. In the second part of this tutorial, I will introduce computational methods to analyze different aspects of given assemblies. In particular, we focus on 4 different aspects of assemblies in this tutorial. Parts fabricability, how to define if a given part shape is fabricable by a specific digital fabrication technique. Parts joining, how to join parts together. Assembly planning, how to assemble a set of parts into the final object. Structural stability, how to test if a given assembly can preserve its form under external forces without collapse. Let's start with parts fabricability. Parts fabricability depends on the selected digital fabrication technique. 3 most widely used digital fabrication techniques are laser cutting, CNC milling, and 3D printing. In particular, laser cutting and CNC milling are subtractive manufacturing since they build 3D objects by cutting material away from a solid block of material. 3D printing is also called additive manufacturing since they build 3D objects by adding layer upon layer of material. The digital fabrication can make 3D shapes with different fidelities. Laser cutting has the lowest fidelity since it can only fabricate 2D shapes. 3D printing has the highest fidelity since it can fabricate 3D shapes of almost any complexity. Laser cutting fabricates a shape by cutting flat sheets with a high-power laser. This video shows the laser cutting process to fabricate 2D gears. Laser cutting has several advantages like high precision, high speed, and supporting many materials. However, laser cutting can fabricate planar shapes only. Due to this reason, the input of laser cutting is simply a 2D shape, for example, represented as an SVG file. 3-axis CNC milling fabricates a 3D object by removing material from a starting block using a 3-axis CNC milling cutter. This video shows the CNC milling process to fabricate a mechanical part. Compared with laser cutting, CNC milling has advantages like supporting general 3D shapes and great mechanical properties. However, it also usually more expensive and dangerous. Since the CNC milling tool can only translate along the 3 major axes, only 3D height field shapes can be fabricated by this technique, which are also called pyramidal shape. Here we show 2 height field shapes that are fabricated with aluminum and wood, respectively. These height field shapes have a flat base. The direction perpendicular to the base is the milling direction, and the surface on top of the base has to be a height field surface. But how to test if a given shape S is a height field shape? Here is the first method. For any point P inside the height field shape S, the line segment between P and the perpendicular projection P prime of P onto the flat base BS lies entirely inside the shape S. This method requires testing every point inside the shape S, which can be computationally expensive. A more efficient method is to shoot a ray from the axis along axis M for any point P prime on the base surface BS, and then compute the number of intersection points between the ray and the boundary of the shape S. The number of intersection points should be always 1 for height field shapes. The third method checks if the long base surface is a height field surface. In detail, for any point P on the long base surface, the angle between the outward pointing normal N of point P and the base direction M to be acute, as shown in this left example. Otherwise, it indicates a cavity below the point P, as shown here, making the shape long height field, as shown by the right example. 3D printing slices a 3D object into many layers and fabricate layers one at a time, from bottom to top, for making a 3D object, as demonstrated by this video. '3D printing can fabricate 3D shapes of almost any complexity, which significantly expands 3D shapes that can be directly made with digital fabrication. One limitation of 3D printing is that it requires support materials for 3D printing shapes with overhangs, which are highlighted in this dragon example. Supporting these overhangs will require not only more materials, but also more printing time. In addition, peeling away these support materials may affect the appearance of the final product. Given a 3D shape, overhangs can be automatically identified. There are two kinds of overhangs, point overhang and face overhang. Point overhangs are points lower than its neighbors, which can be easily identified by comparing the point height. Face overhangs are faces whose normals deviate from the 3D printing direction YP with an angle alpha that is larger than a threshold alpha C. The threshold alpha C depends on the 3D printers and the materials, and which, for example, can be set as 45 degrees. Recently, there is a rising interest in studying new digital fabrication techniques, either for making lower shapes or for better fabrication performance. For example, we can fabricate a sweep surface by hot wire cutting with a flexible rod. The shape of the flexible heated rod is actively controlled by a dual-arm robot when the rod cuts through the material. We can also use a two-pass 3-axis Cnc milling to fabricate double height field shape, meaning that a 3D shape is a height field in both sides. This fabrication technique can significantly reduce both milling time and material waste compared to conventional ones. In the right example, a bunny is 3D printed without using any support material. This is achieved by fabricating the 3D model on a robotic printing system equipped with multi-axis motion. Materials are accumulated inside the volume along curved tool passes, so that the need of supporting structures can be tremendously reduced or even completely abandoned. Path joining. It is a common knowledge that parts in an assembly need to be joined together to make the assembly stable. Compare these two house assemblies. Which one is more stable? It is obvious that the Lego house on the right is more stable than the wooden house on the left, on the external forces. But why? It is because they use different joining methods. In the wooden house, parts simply stack on one another with planar contacts, while parts in the Lego house are connected by friction joints. We call this geometry of material used to connect parts joints. Joints can be broadly classified as permanent or non-permanent. Typical permanent joints include adhesive material such as glue and permanent mechanical fasteners such as rivets. Typical non-permanent joints include screws and woodworking joints. Compared with permanent joints, a significant advantage of non-permanent joints is to encourage parts disassembly and reassembly. Non-permanent joints can be classified as external joints and integral joints. Screws and 3D printable connectors are external joints. They are independent from the parts. Woodworking joints and curved contact joints are integral joints. Integral joints are a portion of parts, meaning that they are integrated with the parts. Integral joints can significantly simplify the assembly process by reducing the total number of assembly steps and assisting parts alignment. External joints can be further classified as conventional joints, such as screws, and customized joints, such as 3D printable connectors. And integral joints can be further classified as woodworking joints, curved contact joints, and planar contact joints. Given joint's geometry, we also can analyze its ability to connect two parts. Given these four joints shown here, we can see that the joint's ability to connect parts became stronger from left to right. So, can we quantify the joint's ability to connect parts? Given a joint, its ability to connect parts can be quantified by the ability to restrict part relative moment. In these four joints, if we consider only translational motion to take out the green part, all possible translational directions for each joint is visualized here. For the planar contact on the left, the green part can translate along any direction in the half circle, while for the tendon joint on the right, the green part can only move upward along a single direction. Based on the motion space, we can quantify the joint's ability to connect parts. When the joint motion space becomes smaller, the joint's ability to connect parts becomes stronger. Now, the question is, how can we compute this motion space, especially when we consider rigid motion? To answer this question, let's start with the simplest case, which is the planar contact. We assume the cyan part is fixed and calculate the rigid motion space of the green part. During the movement of the green part, the constraint is to avoid collision with the cyan part. These collision-free constraints at a point C on the planar contact can be formulated as Vc.n larger than or equal to 0, where Vc is the speed of the point C and n is the contact normal. And the speed Vc can be calculated by using this equation. The constraint for a planar contact can be formulated as these two inequalities for its two endpoints respectively, since we consider infinitesimal motion of the green part. When a joint has multiple planar contacts, we can formulate the constraint for each planar contact, such as C1, C2 shown here, and then we can stack all these constraints to form a system of linear inequalities. The joint motion space can be obtained by solving the system of linear inequalities. For curved contacts, we can use a sampling approach to compute its allowed motion space. In detail, we sample a number of points on the curved contact, list the constraint for each contact point, and stack all these constraints to form a system of linear inequalities. Due to the sampling strategy, our computed motion space is an upper bound of the actual motion space. Recently, there are several research works on studying customized digital joints. In this example, a customized joint is designed for connecting two objects, such as a sofa armrest and a mug, aiming to hold the mug on the sofa. We call such a joint two-way joint, since it connects two objects. In the middle example, 4 two-way joints are designed to build a stable arc with stones. The geometry of each joint is modeled to fit the reconstructed shape of the stones. In the right example, many n-way joints are modeled and planned to build a stable frame structure. Similarly, some research works study customized integral joints. These integral joints can be decorative to enrich the assembly's appearance, or they can be orthogonally connected to make an assembly structurally stable. These integral joints are also possible to have curved contacts, aiming to make a structure stable and easy to assemble. Assembly planning. Assembly planning is the process of creating detailed instructions to combine separate parts into the final structure. Assembly planning is widely used in automated manufacturing, robotics, and architecture. Assembly planning will output 3 sets of information for assembly. First, an order of assembled parts, or assembly sequence. In this example, we first assemble the orange part, followed by the blue, yellow, and green parts. Second, motion to bring each part to its target pose, also called assembly path planning. In this example, for the blue, yellow, and cyan parts, we translate each of them from left to right. For the green part, we translate it downward. Third, utilization of additional resources for the assembly process, such as supports and tools. Look at the intermediate assembly. The blue part is held by using a support in order to assemble the cyan part. Similarly, we need a support to hold the yellow part in the intermediate assembly in order to assemble the cyan part. Disassembly planning is a reverse process of assembly planning. A bijection exists between assembly and disassembly sequences and passes if we consider only geometric constraints. This enables an important strategy for assembly planning called assembly by disassembly. In this strategy, we first compute a disassembly plan for a given assembly, then we obtain the assembly plan by reversing the disassembly plan. The advantage of this strategy is to dramatically reduce the size of the solution space for searching the valid assembly plans. This is because parts in an assembled state have far more precedence and motion constraints than in a disassembled state. Here I introduce a commonly used method to search for a valid disassembly plan. First, we model an assembly with a path graph, where each node represents a part and each edge represents a joint between 2 associated parts. For example, the edge between part P1 and P2 is the joint J1. Next, we compute mobility for each part Pi, denoted as MPI, by identifying joints associated with Pi and intersecting the motion space of all the joints. For example, to compute the mobility of the cyan part P2, we identify its associated joints J1, J3, and J5, which allow P2 to move along -y, negative x, and negative x respectively. The intersection among these joints mobility space is an empty set, meaning that P2 is not movable. We can use the same method to compute the mobility of part P1. Joint J1 allows the part P1 to move along positive y. Joint J2 allows the part P1 to move along positive y2. Hence, the part P1 is movable along positive y. Once we identify all the movable parts, we select one from them. In this example, we choose the movable part P1. Then we remove the part from the assembly and update the path graph accordingly. We repeat step 3 to select a movable part in the remaining assembly, which is the cyan part P2 shown here. and we repeat step 4 to take out the sign part P2. We repeat steps 3 and 4 iteratively until there is only one part left in the assembly. By this, we find a valid plan to disassemble the structure into individual parts. The disassembly sequence is P1, P2, P3, and P4. And the disassembly motion is also indicated for each part. This disassembly plan looks simple because we have made some assumptions for solving the disassembly planning problem. First, we move a single part at a time. Second, we move parts in sequence. Third, once we move a part, we can take it out from the assembly directly. However, this assembly planning problem in general can be much more complicated than this. Classification of disassembly plans. Disassembly plans can be classified as sequential and non-sequential. A sequential plan is also called two-handed plan, meaning that we can always use two hands to disassemble the parts. See the top example. The bottom example shows a non-sequential plan or a three-handed plan. We need three hands to disassemble it. One hand fixes the orange part, one hand moves the green one, and one hand moves the cyan one at the same time. An assembly is monotone if no intermediate placement operations are needed for the assembly. See the top example. The bottom example shows a non-monotone plan. This is because at the first step, we need to move the green part to the right in order to take out the cyan part, shown here. An assembly plan is linear if all assembly operations involve moving a single part with respect to the rest of the assembly. See the top example. The bottom example shows a nonlinear plan. This is because the first disassembly operation involves moving two parts at the same time, as shown here. A coherent plan means that each part that is moved will touch the rest of the assembly. See the top example. The bottom example shows a non-coherent plan. This is because when we move the orange part, it does not touch any part in the rest of the assembly. Disassembly planning is an NP-complete problem. To simplify the problem, people focus on the simplest disassembly plans, which are sequential, monotone, linear, and coherent. They may also focus on simple motions, such as translations for the disassembly. These assumptions significantly simplify the disassembly planning problem. Yet, the cost is that when the planner may wrongly identify an assembly as not disassemblable. This is because although the assembly cannot be disassembled by simple plans, but it is possible to be disassembled by using more complex plans. In recent years, there is a rising interest in studying computational methods to search for complex disassembly plans. For example, search for a non-coherent plan with rigid motions to solve a disentanglement puzzle. Search for a non-sequential plan with simultaneous path motion to efficiently assemble a 3D printed object. And search for a non-monotone plan for assembly mechanical parts compactly put together in a limited internal space of a machine. Structural stability. An assembly with rigid parts is structurally stable if it can preserve its form under external forces without collapse. Given these two assemblies, we know that a Lego house with friction joints should be more stable. But how can we quantify stability computationally? A structurally stable assembly means it can be in equilibrium under certain external forces. Taking this assembly as an example, it is in equilibrium under gravity. Static analysis is a widely used method to test if a given assembly is in equilibrium under a certain external force. However, a lateral force, such as those from the wind, can easily make the assembly collapse. In practice, an assembly should be in equilibrium not only under gravity, but also under lateral forces. Tilt analysis is a process to quantify this lateral stability. In an extreme state, an assembly can be in equilibrium under arbitrary external forces. We call this structural stability state as interlocking. Comparing these three states, we can see that the assembly becomes more and more structurally stable. And the cost is that the parts geometry becomes more and more complex, since more restrictive joints are used to connect the parts. The state-of-the-art static analysis method is the rigid block equilibrium method. Given the geometry of a 3D assembly, a static equilibrium state means that there exists a network of interaction forces between the parts that can balance the external forces acting on each part. Here, the interaction forces on each contact plane are discretized as forces positioned at each of the tags of the contact interface, modeling a linear force distribution across.
Can you hear me? Yeah. So because we started this section a little bit late, so I will skip some of the pause and start now to catch up the time. Is it okay? Everything fine? Just a second. So hello everyone. My name is Ziqi. Ziqi Wang. I'm from ETH. I'm now a postdoc there, and I will present my part, the second part, which is talking about the computational design of assemblies. So 3D assemblies are ubiquitous in our daily life, such as toys, furniture, and architecture, which discussed in the first section by Peng. And the purpose of my part is actually use the computational approaches to design assemblies that can satisfy some predefined goals. And specifically, most design problems actually have two main components, the part geometry and the design objectives. So look at this very simple example here. This T-shaped assembly is parameterized by one variable theta, which allows the blue part to move horizontally. And our goal is to make the assembly stable under gravity. Of course, the left one is not stable, and the goal is to make it like the right one. So in the classical forward design framework, designer try to tune some design parameter like this theta to make the assembly more stable. However, a one-time adjustment may not be able to find the correct parameters. We have to do many iterations until the objectives are achieved. So this kind of forward design framework has some limitations that make it somehow inapplicable for many design problems. So the first one is the design space could be enormously large, beyond the capacity of human designers. Like making this in talking cube with only 6 parts. In total, we have 6 to 64th power possibilities. So finding one solution is very challenging using this kind of try and error method. Second, some design problems may have multiple design objectives, and these objectives may be contradicting, like assemblability and stability. At the left, the assembly with planar contact is very easy to assemble, but not stable. At the right, the assembly with single direction joint is stable, but very hard to assemble. So you have to make trade-off, which is very hard, especially for the inexperienced designers. Lastly, the process of evaluating some objectives could be very time-consuming, like computing the maximum internal stress of assembly. Inefficient evaluation reduces the number of iterations the designers possibly can do. So the computational approaches instead find these optimal parameters to make this T-shaped assembly stand in the gravity automatically. So we call this method the inverse design. In general, for part geometry, besides the parametric modeling, which use continuous variables, some other researchers also focus on solving discrete problems like building Lego. So for the discrete geometry, the problem usually solved by some searching algorithm. And for the continuous geometry, designers usually use the gradient-based optimization to find the solution. So for the objectives, besides the stability we just introduced, we also have the assemblability, which determines whether the designs can be assembled either by hand or by a robot arms. We also have the fabricability, which determines whether the design can be fabricated by some machines. And functionalities, for instance, this assembly can be reconfigurable to many different forms. But in this part of course, I will only focus on the stability, and for the next part, our colleague Marco will explain how to improve the assembly's fabricability, the second image, in the next part. So we all know, without stability, a structure is not physically buildable. For some wooden architectures and masonry structures, they don't rely on any external fasteners or glues to be stable. So to design this kind of structures bring a huge problems or challenge for designers, and we are going to tackle these problems using computational approaches. So besides the most common type of stability, the stability under gravity, this talk will also cover other type of stability, such as lateral stability, like wing load, and stability during assembly, so you need to reduce the amount of scaffolding during the assembly, and also the global interlocking, which can be any arbitrated the force and torque. So we draw this stability spectrum. You can see from the left to the right, the structure become more and more stable until it cannot be assembled or disassembled. Okay, so let's have an overview of my part. So I divide my part into three. First, we will explain a general workflow for design stable assembly using shape optimization. And then we will specifically explain how to use this framework to design structures that are stable in gravity. We have actually two methods, one using the statics and the other using the kinematics. And we also briefly explain how to implement friction. In the last part of my presentation, I will briefly explain how to modify our workflow to design assembly with other type of stabilities, such as lateral stability, stability during assembly, and globally interlocking. Yeah, this is the scaffold-free assembly. Okay, so let's move to the first part of my talk. So I will explain actually an algorithm template, so you can apply it to solve a very broad range of stability design problems. Again, we emphasize the problem is to make an unstable assembly stable by changing its part geometry. Because many designers use this parameterized part geometry, So we can view these design problems as continuous shaping optimization. So optimization is like a hike in the mountain. You need to find a path that can make you down quickly. Abstractly, we measure the quality of our design using an energy function E, which is just a function of the design variable theta. Our goal is to minimize this energy E by iteratively updating the design variable theta. At each step, we can either update the parameters by randomly take a downhill direction, or we can take actually the steepest direction, which is the negative gradient direction in our case, and it's turned out to be usually very fast than a random direction. So this is the general design workflow of probably most of the stability optimization, and it had the 4 steps. The first 2 steps are about formulating the problem as an energy minimization, and the last 2 steps are using the sensitive analyze to find the optimal value of this energy minimization. Okay, let's look at what exactly the 4 steps. So before introducing the exact energy formulation, we need to first compute some necessary geometry properties, such as contact points, contact normals, path centroid, path volume, using the given design parameters. Then the second step is to, after having this necessary geometry information computed, our problem then turned out to be how to formulate the problem as an energy minimization, which brings up to a very important concept. We call it infeasibility. The infeasibility, or we call it infeasibility energy, measures how unstable the structure is. For different stability problem, we will have like using different infeasibility formulation. But for this specific 2-part problems, assuming the blue part is fixed, the structure is stable only if the centroid of the green part stay inside the contact polygon of the blue part. Apparently, for this structure, the centroid of green part does not meet this stability requirement. But we can measure how much is disobeyed this requirement by measuring the distance highlighted in red. The larger the distance is, the more unstable the structure will be. So our goal is to minimize this infeasibility energy. But like any shape optimization, you need to compute the gradient. So that's why we have, in the third steps, we need to find the gradient information with respect to the design parameters. But sometimes directly compute the gradient is challenging, especially for a more generated stability problem discussed later. So we often compute this gradient with respect to some intermediate variables and then use some chain rules to compute the actual gradient. It's also like the auto differentiation. But in the last step, with the help of the gradient, we can finally compute the optimal value using the classical gradient-based numerical optimization. Actually, there are 3 numerical methods, and I personally prefer the quasi-Newton method like BFGS, LBFGS, which only requires the first-order derivatives, and it performs better than a simple gradient descent method. For the Newton method, it's actually run faster, but you have to compute the hash, and sometimes it's challenging. So let's move to the second part. Since we already discussed a template, then we need to apply it to specific problems. And here we only focus on the stability under gravity. Let's make some assumptions before I introduce the method. First, we assume all parts are rigid. And second, at the moment we ignore the friction, but we will discuss in later of this section. And third is the bottom blue part we assume is fixed. This condition just simplifies the design problem, and the stability of the design is independent of the material property of the parts. Because we don't have friction, we don't need to consider the friction coefficient of the contact interface. So it's stable for ice or also stable for stone if you use our method. At the end of this part, we will also briefly explain how to consider friction. So first, let's recap the basic tools of checking whether a given structure is stable under external forces. We can use this called rigid body equilibrium method, RBE. It actually has 3 parts. First, it has the force equation, force balance equation. Just ask for all the sum of internal forces and external forces are 0. Second, because it's rigid body, so you have also consider torque. So we have asked all the internal torque and all the internal torque to be equal to 0. Here, the gravity is not in the equation because we can set the rotational center to be the path centroid to remove the torque generated by the gravity. Third, it's like all internal forces should be compression force only, acting on the contact interface. Yeah. And we also don't need to set this kind of force and torque balance equation for a fixed part. For the blue part, we don't need to actually set up it because it's fixed. And this kind of formulation will give us a check, say yes and no to this structure, whether it's stable or not. However, it will not provide actual infeasibility energy we showed just a minute ago about how unstable the structure is. So we need to find a good infeasibility energy formulation for this kind of problems. So how? So in this presentation, I will explain actually 2 ways of computing the infeasibility energy using either statics or kinematics. But let's first look at the force-based approaches which we can derive from the RBE method. The main modification of the RBE is to split the contact compression forces into 2 parts. The positive part and negative part. We keep the force balance and torque balance equation unchanged, but for the non-negative constraints, we ask for both positive and negative parts of the contact force to be greater and equal to 0. Here, the negative parts of the force, like a tension force, that actually pull the 2 parts together. So an unstable assembly can now be stable in this new definition. However, these tension forces are not realistic in practice, especially if you don't care any glue or external fasteners, it's not exist. We need to minimize this amount of tension in the system, which is used to make the force and the torque balance constraint valid. So the minimum value, the tension value, provides actually a good formulation for the infeasibility energy. When there's no tension in the structure is stable by definition. Further, if we just collecting all this balance equation, and you will see actually the problem turned out to be a quadratic programming that can be solved by many existing libraries, such as Mosaic or OSQP. Then the next step is actually how to compute the derivatives of the infeasibility energy with respect to the design parameters. We can draw actually the computational graph of the infeasibility energy. So the first is the design parameters that are computed using the basic geometry computations, such as contact points, normals, part centroid, and part volume, all can compute it from the design parameters. Then this geometry properties can derive the coefficient matrix of the quadratic programming, which used for the infeasibility energy measurement. We can compute these derivatives either using hand-derived formulation, or we can use the auto differentiation to compute. But there's one last step that to compute the derivatives of the quadratic programming optimal value with respect to its coefficient. Sometimes I don't see any, or it's not so obvious that AutoDiff can do this, so we need to derive by our own. To solve the problem, we need to use the fact that when there's no inequality constraint in a QP problem, we can actually derive a closed form formulation for these specific problems. If you have the closed form solution, you can easily compute the derivatives. But how to get rid of the inequalities in the system? So we use this fact, like locally change the geometry will not alter the forces value too much. Like here, we only move the blue part a little bit to the right. The force will only change a little bit. So if a force are already close to 0, we just set it to 0. Otherwise, the inequality constraint is valid if you move a little bit of the part's geometry. You will not disobey or change the inequality constraints. So we can just completely remove it. So without this inequality constraint, but only keep the forces that very close to 0 as an equality constraint, we can actually derive a closed form optimal solution for the optimal value, and thus compute the gradient with respect to the coefficient of the QP problems. And in the end, we can just use the chain rules from the left to the right to compute the infeasible energy gradient with respect to the design parameters. And this is the result from their paper. So they can make not the pillar thicker, but also move the position of the pillar to make the structure stable. But there's actually some limitations for the force-based equilibrium method. The first one is it's very hard to test global interlocking assembly. If you don't know what it is, it's basically assembly that can withstand arbitrate forces and torques. You cannot exhaustively test every configuration of these external forces using the force-based method. Second, for non-planar contacts, you have to sample the surface, which may be less efficient. Therefore, we consider another type of equilibrium method, which use kinematics. The goal is to measure the grain part's collision-free movement. We only consider the infinitesimal motion, which is composed of rotational part and translational part. So it had a 3 degree of freedom in this setup, but for 3D, it has 6 degrees of freedom. Then we can define the motion space of this green part to be all collision-free infinitesimal motions that can take the green part off from the blue part. In 2D, the green part has only 3 degrees of freedom, two translation, 1 rotation. So the motion space is actually a cone in 3D. The motion space V is called the joint motion cone of the contact between the green part and the blue part. To compute this joint motion cone V, I think it's discussed in the first session, but I will quickly recap it. So it basically sample the contact surface into pairs of contact points on the contact normals. So for each contact point, the non-collision constraints requires that the dot product between the instant speed of the contact point VR and the contact normal N should be non-negative. And for the velocity VR is actually computed by the sum of the rotational component omega cross product with the rotational arm R plus the translational part V. And then you can set up the equation and compute the motion cone. So we combine all the non-collision constraints for all contact points. We can draw actually the motion cones for all this type of joints. You will see that the volume of the cones decrease from planar joints to single direction joints. It's more intuitive because planar contact have less constraint for the part motions. But for the single direction joint, its motion cone is actually the plus y vector. But if you use the force space equilibrium method, you have to sample these 6 points. So apparently the kinematic based method is more efficient because it only uses 1 vector as a motion cone. But however, the motion in the motion cone is not always physically achievable or plausible. Like translating the green part along plus y direction is collision free, but won't happen in the gravity. The reason is that the green part's movement should decrease its gravitational potential. The dot product between the instant velocity of the center of mass of the green part we see and the W should be positive. We can reformulate it using an infinitesimal motion V hat and the generalized force W hat. So combining these 2 physical plausible constraints and the non-collision constraint into one system, the assembly is equilibrium only if the system does not contain any solutions. So we actually can visualize these constraints and show it here. So the physical plausible constraint is defined by a half space, and the non-collision constraints are defined by a cone. If the intersection volume is not empty, the structure is not in equilibrium. But this test will only give us a yes and no answer, like the RBE method we discussed earlier. But we need the infeasibility energy, so how to do it? So this, just by adding a regularization term, V transpose times V in the objective function, along with the physical plausible constraint, the W times V. It basically is like a gravity potential plus minus a kinematic energy. And using this energy with the constraint of the motion cone, we actually can compute the infeasibility energy. And it turned out that this energy becomes zero when the structure is stable under gravity. The measure also can be extended to multiple parts assembly. The non-collision constraints now just set for each pair of adjacent parts. The objective function is almost the same. We just stack all the parts, generalized velocity, and gravity to get the V hat and W. So by collecting all the constraints, we also can get a similar quadratic programming, but with inequality constraints. And we then can use the sensitive analyze to compute the gradient. But if you want to learn more, please refer to the papers. If this is not very intuitive, we can actually prove the correctness of this kinematic-based method using the fact that the kinematic and static actually are dual problems. So if you compute actually the dual of the equation or the optimization problem I just showed, you will see that it actually go back to the first domain, and the method is actually penalizing the actual forces or torques acting on each part to make the structure stable. For the force space equilibrium method, is actually penalizing the unrealistic compression, unrealistic tension force acting on every contact interface. So one is for every interface and one is for every part. But they achieve the same goal to make the unstable structure stable by adding unrealistic forces. Another advantage of this kinematic-based method is that it can provide a good abstraction of the original assembly for structure stability optimization. We find that either the two classical ways, either using the part graph, which each node is represent a part and each edge represent a contact, or the exactly part geometry have some limitations for stability optimization. For the geometry-based representation, it often had redundancies. For example, this assembly with just one singleton joint or two singleton joints have the same structure stability, but they have totally different geometries. Second, the part graph is very lightweight, but it actually doesn't have the complete information for the structure stability analysis. Here, the two parts have the same part graph, but totally different structure stability performance. Therefore, we would like to use a new motion-based representation, which is both lightweight and sufficient for structure stability analysis. So this motion-based representation is obtained by augmenting the assembly's part graph with motion cones at its edges. Here, the contact C21 is an edge from P2 to P1. We just stored the motion cone we just discussed earlier, this width C21 at its edge. Having all the motion cone computed, the motion-based representation is able to measure the structure stability of given assembly without actually knowing the exact part geometry. So instead of directly finding the part geometry using optimization, we can first find a stable motion-based representation by using numerical optimization. We then find the part geometry locally to realize this motion-based representation. since we decouple the motion and the geometry, this method sometimes is very efficient and also very flexible in handling a wide range of problems. This is a result using this method. Here, our goal is not just to make the structure stable, but also make the assembly easier. So we use this kind of cone-like or curved joints or cone-shaped joints to make the assembly easier. To increase the amount of insertion direction you can use for each assembly step. So there is one missing part for the previous method because we haven't discussed anything about the material property, especially the friction. We can provide extra forces to prevent the structure from collapse. So without friction, our test is more conservative, so it's valid for most of the case, but it will exclude some solutions. However, need the friction for certain assemblies, particularly for the assembly using snap joints like Lego. The stability completely rely on the friction to prevent the two blocks from detached. Simple and most widely used friction model is the Colombo friction model. The resultant forces and so the resultant forces is actually composed of the friction force Ft and the compression force Fn, and these resultant forces should be within a friction cone, characterized by the friction coefficient mu. But for a specific structure, especially like Lego, because the normal contact forces are due to the elasticity deformation, which is usually a constant value. In this case, the size of the friction is no need to use the friction cone, but just within a range that's determined by a friction coefficient, because the contact normal force is a constant. But there's one specific drawback of this Colombo friction model, especially for the mainstream structures, that it can actually produce unrealistic forces. For example, in these three parts assemblies, on the left, if the two side vertical parts just merely contact with the vertical part, the horizontal part, it should not create any compression force between them. However, there exists such force configuration, like the image I just showed, that the structure is actually stable because of the friction. So you can create unrealistic compression, then this unrealistic compression create unrealistic friction to make the structure stable. But if you still feel this is not so obvious, we can see the three-part examples on the right. It's definitely like this will be unstable, it will definitely fall. But if you use the friction model, I just explained the Colombo friction model, with some proper friction coefficient, you can actually find a stable force configuration that make this structure stable. But this definitely physically non-exist. The reason for this is because the Colombo friction model is not reflect the true physics. So we need to act actually more constrained for the friction. First, we have to use these complementary conditions, which basically said if two parts have the tendency to move away from each other, this should not have contact forces. The second is called the maximum dissipation requirement, meaning that the friction should create the maximum amount of work. For this simple 2D examples, the friction always should point to the opposite direction of the part's relative movement. So having both of these conditions, it's actually possible to exclude the sliding failure, the failure I just showed, to make the test result more close to the realistic. However, it will make the problem non-convex, therefore making the test very hard. But it's very good research direction for you to actually find an efficient and accurate enough analyzing method for this kind of friction problems. Third part of my presentation is about designing for more type of stabilities. Let's check this lateral stabilities. In practice, equilibrium under gravity may not be sufficient for since the assembly could be exposed to different loads or force. Therefore, we can further optimize assembly geometry such that it can be in equilibrium for a cone of gravity directions. Still, let's go back to the template of our workflow. Actually, the most important part is actually how to formulate the infeasibility energy that can be used for lateral stabilities. Here, because the tilting the ground is equivalent to tilt the gravity direction, we can use a cone to represent the tilt stability. So each vector inside this cone is a gravity direction for which this igloo is in equilibrium. We all know that our equilibrium, or either the force-based equilibrium method or the kinematic-based equilibrium method is a linear system. The constraint is a linear system. So this cone should be convex. And the structure stability is just the minimum of the maximum tilt angle in all tilt directions. Or the lateral stability is actually this minimum and maximum tilt angle. But how to enlarge this gravitational cone or this lateral stability is what we need. And for example, here, we need to include red gravity direction into the cone. So using the common infeasible energy for just one gravity direction, we can have these two values. For the blue edges, because it's inside the cone, so the infeasible energy is 0. But for the red arrow, it's outside of this cone, so the infeasible energy is non-zero. So from the previous slides, we know we can use the sensitive analyze to compute the first derivative of the infeasible energy. Then we can use some Cauchy-Newton method to solve this energy minimization problem. And we can make the red arrow into the cone. But there's one problem, because the cone may not be increased. It just can shift to the left, but the volume of the cone may not increase. So the worst case of this cone, which measures the lateral stability, may not be improved. So to enlarge the feasible cone, we actually have to minimize the energy for multiple directions simultaneously. And we also need to consider some constraints. Like here, it's like the contact between two parts should be at least some values to make sure the structure is valid. And we can use the fact that this gravitational stable cone is convex. So if we can make sure the 4 arrows is inside the cone, then the prism shape defined by these 4 arrows will at least inside the new cone. Then we can say we increase the structure tilting stability or lateral stability. And this process can be repeated for several times until the stability stops increase. And here the animation show that this igloo can be tilted a lot until it crashes. Okay, then the next type of stability is the scaffold-free assembly. The goal of the scaffold-free assembly is to make the assembly stable during the assembly process. Like this leaning tower, at every assembly stage, the tower can just stand without actual hands holding it or any scaffold from the table to hold it. Such assembly can save a great amount of scaffolding, and especially it makes the assembly faster, assembly process faster, and actually can be executed by robots. Again, the problem is how to formulate the infeasibility energy for these specific settings. Here, the infeasible energy is just the summation of all the infeasible energy at each assembly steps. By given assembly step, you can always compute this infeasible energy, then you can follow the same steps as a gravitational equilibrium method to solve the problem, to compute the derivatives, use the optimization to find optimal value to make this structure stand for every assembly steps. So the last type of stability is the global interlocking. To understand what's the definition of global interlocking, Peng already told this, I just quickly recap it. It's basically you have 2 assemblies, and only the assembly at the right is global interlocking. And we call the part P5 is the last pieces, the key part. The reason for why the right one is interlocking, the left one is not, is because if we fix the key part P5 and any of the rest part P3, no part should be taken out from a global interlocking assembly. But apparently, the assembly at the left does not meet this requirement, so it's not global interlocking. But examining whether assembly is interlocking or not it's very time-consuming in a classical way. We actually have to check every parts and subsets of parts to see whether one of them can be taken out from the assembly. So in this section, because we always deal with these discrete geometries like voxels, we cannot continue use the continuous optimization method. We have to use a completely different ways, which basically for most of the state of the algorithms, you use the search method to find the solution. For the first paper I discussed is the voxelized. They use voxelized input 3D shape, and they propose a shape decomposition algorithms to construct interlocking assemblies, like the left bunny. And later, they extend their method to handle like smooth, non-voxelized shape, but the internal structure is still voxels. The core idea of their paper is to iteratively extract pieces while enforcing the local interlocking conditions for every 3 consecutive pieces. For example, here, the P1, P2, R2 is locally interlocking in figure C, and then P2, P3, R3 is locally interlocking in figure D. Repeating this process until we find the final interlocking assemblies. See the figure E. We call this step the recursive interlocking assemblies. But when the input is not composed of voxels, but just a set of parts without joints, this voxelized decomposition method may not work. For the furniture design, Fu and their colleagues connect parts with orthogonal joints to make the assembly interlocking. Some later extend their method to design interlocking polyhedrons to fill the internal space of a large 3D printing model. Their polyhedrons are assemblies of 2D laser cut plates connected with non-orthogonal joints. Yao and their colleagues later also use snap fit joints to construct interlocking shells to save material and printing time. One typical approach for this kind of joining planning problems is to construct so-called local interlocking group, LIGs, which are subset of connected parts that are locked by a specific key in the group. Once multiple LIGs as well as their blocking dependency between them are made, the resulting assemblies are guaranteed to be global interlocking. However, the limitation of this LIG method is that the explored searching space is restricted by a small subset and all possible interlocking configurations. A much larger design space can be obtained by using this directional blocking graphs. So basically, we can, it's also discussed in the first section, but I just recap it, is that we can present the parts blocking relations using this family of DBGs. And we can use efficient graph analyzing tools to test and compute the interlocking arrangement of the parts. And it works, and this method provides a general framework for design interlocking assemblies, works for both voxelized shape and also joint planning problems. So we can actually, just in a word, so we can just easily test whether the left assembly is globally interlocking or not by just checking the surrounding connectivity of these two graphs except the key. So if the two parts except the key, to a graph except the key part is surrounding connected, then the structure or the assembly is globally interlocking, which you don't need to actually do the subset of parts, this exponential checking now. You can do it in a linear time. But how to use this graph to design the global interlocking assemblies? Here we take this 5x5 square as an example and show how to partition it to get a 5-part interlocking assemblies. First, we have to construct the key for the assembly. There actually have many possibilities, and we only select a few candidates. Then our problem is how to design the 3-part interlocking assemblies by partitioning A1. In the previous slides, we show the DBGs, and we also show that they can actually be used to check whether it's global interlocking or not by verifying its surrounding connectivities. So we can use this graph to design our, to use the graph to guide our design. So the red part in the X direction is blocked by both sides. So we just create these two directed edges in G plus X. But for the plus Y direction, the red part can be moved out vertically in up direction. So we just add one direction edge from the green part to the red part. So with the help of this directional blocking graphs, we can actually completely ignore the geometry for the moment. And to get a three-part assembly, we split the green nodes into two parts. The dot ellipse indicates the original green node before splitting. So our goal is actually, after the splition, we want to maintain the graph's surrounding connectivities by just adding more edges or shift some of the edges. If we can maintain this surrounding connectivity property, then we can maintain the global interlocking of our assembly after decomposition. So we first choose the internal blocking relations, which just this red edges. And then according to these internal blocking relations, we can distribute the external blocking relations, the blue edges, to the two split nodes. Here, except for the key, every part is in one of the strongly connected components for every DBGs. The key is the red, so you have to ignore the red, and you will see that they are in strongly connected components. Now, we find a valid directional blocking graph. The next subproblem is to find the corresponding geometries. It's similar to the previous steps. We also call it the geometry realization stage. But we skip the details. If you're interested, you can see the paper. Suppose we can find actually one design that satisfies the directional blocking graphs. But this is because it's not one-one correspondence, you can find many of these geometry realizations. And for this specific graph, just show all candidates, but some candidates may not be able to generate more number of parts in talking structures, especially like this A4. It cannot generate any more parts in talking assemblies because whatever you decommodate the green parts into two, it will broken into two strips that definitely can be moved from the assemblies. So the structure cannot be global in talking. Then you have to do backtracking to the A4 sibling, A5. And luckily, we can find its child, which has 4 parts, also in talking, and we can continue it until we find this A8, which basically a 5-part locking assemblies. And we then stop searching and output this result. And here is an example showing that we can do 3D interlocking docks. But here, we also can add more constraints like the features of the docks. We ask the tails, the ears, and also nose of the docks to be one part. So the designer can have more flexibility. And the previous method have used customized blocks. So every block is different. But we want to actually reuse some of the blocks to save the cost and to make it environmental friendly. And Zhang and their colleagues actually designed a set of 9 tailable blocks with integral joints. They call it the interlocking voxels. And using some hierarchical and layer-by-layer assembly order, these blocks can build up a voxelized assemblies that actually global interlocking. Just some conclusion of my part. So first, I discuss a general workflow or template for a wider range of stability optimization problem. Then we just show a specific shape optimization problem for stability under gravity, and we show actually 2 ways to formulate the problem using force-based or kinematic-based method. And in the second part, we just show different other types of stability like lateral stability, scaffold-free assemblies, global interlocking assemblies. Thank you. So we will have the Q&A in the last part of the session, and we are going to the third part of our talk, which is about the computational assembly for fabrications.
So, hello everybody. Welcome to this third part of the tutorial on computational assemblies. My name is Marco Livesu from CNR. And in this third part, we're going to spend about 50 minutes to talk about shape decomposition when it is intended as a mean to overcome the limitations of digital fabrication hardware. And in particular, during this presentation, we're going to focus on 4 fabrication technologies, which are 3D printing, CNC milling with 3 or 4 axes, laser cutting, and also casting and molding. So we're going to see how shape decomposition can be used to facilitate the fabrication with these 4 different approaches. One remark that I would like to make since the very beginning is that, differently from the previous parts, in this case, the computational assemblies are not fabricated because we have an artistic or functional intent, but because we want to overcome the limit of our fabrication hardware. So essentially, we have a shape, an object that we would like to fabricate, and our hardware will not allow to fabricate the object as it is. And so we're going to see how, through decomposition, we can actually split a complex object into simpler pieces that can be fabricated. And in this regard, the algorithms must be designed in order to address constraints which depend from the hardware, and not only on the specific fabrication technique, for example, 3D printing, but on the specific hardware. Here in the picture, for example, you see 2 3D printing machines which work with the FDM, so they deposit fused filament, and so they essentially apply the same fabrication technique, but they have different sites. And so depending on which printer you use, you're allowed to fabricate smaller or bigger objects. So decomposition can be used to address this kind of constraints. And these constraints can be either soft or hard, depending on their nature. For example, if we talk about the size of an object, this is an hard constraint, meaning that if you do not have a printer that is big enough, or if you're not allowed to split your object into pieces that are small enough, you cannot just proceed with fabrication, and it's a major failure. Other constraints, for example, regarding the quality of the surface, the amount of supports that you may use, are soft, in the sense that even if you do not fulfill all your requirements, you will still be able to fabricate something. So that's the major difference between hard and soft constraints. Another important thing to remember is that when we talk about shape decomposition for fabrication, we must remind that shape decomposition is just one of the possible ways to address constraints that are imposed by the fabrication hardware. For example, mesh deformation is a valid alternative. And here you can see an example from a paper in 2015, where just by changing progressively more the shape of the object that you want to create, you're actually reducing the amount of supports that are needed for the print. So that's another way to address the constraints of fabrication. And also reorientation, so changing the position of your object within the printing chamber can be a valid alternative. And here you can see that a simple shape, depending on how it is positioned, it will have less or more staircase effect. It will be necessary to put none, more or less supporting structures for the overhangs, and it all depends on the orientation. So even reorientation, which is probably the simplest thing that you can do to tweak the fabrication, can be a valid alternative to shape decomposition. But in this presentation, we're going to focus only on methods that pursue these constraints through shape decomposition. And so let's see a bunch of examples, a bunch of reasons why shape decomposition can be used for manufacturing. First of all, as I said, a major problem is the size of the printer. Especially the cheap printers are actually very small. And so if you want to create something that is big enough, for example, for you to sit, if you want to fabricate a chair, you need to decompose your chair in different pieces, and then you reassemble them together. That's a work called Chopper from SIGGRAPH 2012. Major class family of algorithms aim to decompose an object to control its geometry. And here it's all about essentially the angle that is formed by the local orientation of the surface, so the surface normal, and the orientation through which you will deposit or carve away material, depending on what type of fabrication technique you are using. As we will see throughout this presentation, this angle And the relation between these two directions is actually of paramount importance for pretty much any fabrication technique. For example, we know that if we have a height field geometry, we can 3D print the object without support structures. And we can also fabricate the same object using 3-axis milling machine, because the drill bit can essentially reach any point of the surface without hitting in other parts of your object. Whereas if you have an object like this, in which you have some parts that are overhanging, so they are hidden through the direction of manufacturing by other parts of your object. In this case, if you go for 3D printing, you will need supports to sustain essentially this part of your object when you fabricate it. And if you want to go for example, 3-axis milling machine, this is a major failure because you will not be able to carve away essentially this material in yellow. So in this case, shape decomposition can be used to split this object in smaller pieces that do not contain overhangs, such that you can create your object as an assembly of height fields. For CNC milling machines, there is also the version where you have one axis more, which is one rotational axis. And also in this case, essentially you still have sort of an height field constraint that it is expressed not with respect to a single machining direction, but with respect to a rotational axis. And there are methods in the literature to decompose the object such that you have alternative positions of your object where you can reach the surface and carve away the material for axis milling, for example. Recently, another idea of height fieldness was presented. This is a paper from SIGGRAPH 2020, and is what is called the double height field. The double height field is essentially a piece of geometry that can be fabricated with a 3-axis milling machine in 2 machining passes. The idea is that you need to be to fulfill the height field constraint from 2 opposite or almost opposite directions, such that you first carve material from one side and then you flip your object and you carve material from the other side. And so this method was presented essentially to take an input an object which is not an height field, not even a double height field. And the goal was to decompose this object into the minimum number of double height fields that could be fabricated with this technique, such that, again, recomposing everything together, you can create your complex object, for example, with wood. In laser cutting, you can only fabricate things that are flat on the plane. And so if you want to fabricate something which is 3D, so it's inherently not flat, you need to find a way to flatten your object in the plane. And this can be done, for example, with a sort of a UV mapping. And in this case, for example, this idea was used through cylindrical parameterization to flatten different patches of the surface of your object into the plane through a cylindrical parameterization, and then to laser cut some fabric with some zippers, such that when you close the zippers, you actually resemble your original shape. So that's another decomposition aimed for a particular kind of fabrication, which is laser cutting. Another technique which is very popular is casting or molding. Here, essentially what you do is to create pieces that leave an empty void whose shape is the shape that you want to fabricate, such that you fill the void with some material and then you open your cast and you get the wanted shape. In order to be able to open the cast and detach the 2 pieces in order to reveal the object that you want to create, essentially you want that the shape of these objects are height fields, such that this extraction can be performed without having collisions. And in this case, again, if your object is complex enough, it's very hard to find a rigid mold that can create the whole thing. And so you may want to decompose a complex shape like the bunny into few pieces that, if taken alone, can be fabricated with this technology. And a variant of this is that when you have a cast, a mold, which is non-rigid. For example, it's done with silicon. And in this case, you have some more degrees of freedom because you can actually deform your object. And so even if your mold is not a perfect height field, you can still manage to push away the parts and to just deform them enough to complete the detachment and reveal your shape. And it's still a matter of finding a suitable decomposition that exploits this ability of the material to deform up to a point where you can still detach the mold components and reveal your shape. Other important applications of shape decomposition regarding, for example, the surface finish of your object. For example, in 3D printing, we know that 3D printing is also called layered manufacturing. So we know when we fabricate objects by depositing one layer of material on top of the other, and this layering effect can become extremely visible. And in literature, there were proposed methods to decompose the object in order to reduce as much as possible these artifacts given by the layering process. The idea essentially is that when you build something with 3D printing, whenever you're building something which is nearly vertical with respect to the fabrication direction, the error that you have in approximating your geometry is quite small. But when you go nearly horizontal, like in this case, the error that you commit, so that the part of shape that you're actually not creating becomes much bigger. And so the goal of this decomposition strategy, for example, was to reduce as much as possible nearly horizontal portions of the surface, such that the approximation of your object eventually will be of higher quality. Another interesting avenue for research is the material consumption. Given that in 3D printing, in many cases, you need to use external supports because you have overhangs in your object. If your objects are complex enough, one of the typical goals is to reduce as much as possible the amount of supports, because then you save material and also printing time. And in this case, algorithm for shape decomposition aim to decompose objects into simpler pieces that require either a tiny amount of supports or no supports at all. And this is the case, for example, for the pyramidal decomposition, which is nothing but an height field at the end of the day. And if you decompose a complex object like the horse into pyramids, you can fabricate every single piece almost without supports. You have just a few supports here for the head of the horse. And so you will save a lot of time because you don't have to fabricate all these structures, and also material, because this is material that goes away and will not contribute to form your final shape. Supports are a problem for many reasons, not only because they waste material, but also because once you fabricate an object with some supports, the action of detaching them from your object can create a number of artifacts that you can see, for example, in this image. So in literature, there is a variety of methods that decompose the shape just to, well, first of all, reduce as much as possible, as for the application before, the amount of supports, but also to try to hide the contact point between supports and the object in the least visible parts of your shape. So essentially what happens here is that you have sort of a saliency map that allows you to understand what are the most interesting portions of the surface of your object. And those are the portions of the object where you do not want to position supports, because then you know that once you detach them, you will have some artifacts on the surface, and so you want to avoid that. Other important application of shape decomposition for manufacturing is when you have an object which is complex because it's composed of different colors or different materials, and you have a cheap, for example, 3D printer, which operates only with a single filament. So the most you can do is to create a monolithic object that is composed only of one color or one material. And if this is the case, what you can do is to decompose your object such that every single piece that you're going to print will be composed of an homogeneous material. And so you can just, for example, change the color of your filament when you print the various pieces, and then when you assemble them together, you get a multicolor object. In this case, you're essentially solving a form-finding problem because you do not know what is the shape of the object that you're going to create. You just know that you want every single piece to retain the color that you had in the input object and to be assemblable, such that you can actually recompose the different pieces once you are done with the printing. Similar problem, assemblability. So you have an object which is again represented by different colors or properties on the surface. You know how these pieces are going to be composed all together, and you need to understand what is the shape of these objects in 3D, such that you can actually follow this assembly plan. And this can be done, for example, by extruding these objects through the direction that is indicated by the arrow. and through mesh booleans find these volumetric pieces that can actually be fabricated. Collision avoidance. So for sophisticated 3D printing techniques like this one, in which essentially you have the extruder that is steady in its position, and you have a robotic arm which is moving your object in order to choose where to deposit the material, one of the major issues is that you need to avoid conflicts or collisions between what you have already created, so the parts of the body that were already printed, and what you are going to fabricate. This is a problem that typically you do not have in 3D printing because you go flat layer per flat layer, and so because everything is flat, the extruder can never hit anything that was already created. But in this case, actually, the major problem is to avoid these collisions. And so here, what you have to do is to solve a shape decomposition problem where you are operating at the level of the slices, where you want to deposit the material, which are not going to be flat, but are going to be curved. And therefore, you need to explicitly take care of avoiding these collisions. Last application that I mentioned is packing. This is typically the idea that you have some object, you have some box that you want to use for shipping, and you want to fit your object into the box. And this can be done typically by splitting the object, and the goal is to essentially save as much space as possible, such that the assembly of your packing is as tight as possible, and you do not waste material. And also for shipping, the smaller the box that you use, the better, because you pay less for shipping. So that's another goal typical of 3D manufacturing. And there are many others that I'm not mentioning here, but essentially what I wanted to make is the point that shape decomposition for fabrication is used in a variety of different ways. And so it's very important to understand how these methods works. So in the remainder of the presentation, what I'm going to do, rather than taking every single algorithm and describing it, I would like to discuss what are the major ways these algorithms works. Because when you study the literature, what arises is that all these methods more or less rely on similar approaches. So I'm going to try to factorize this information and to organize it. Before we go into this, I would like to spend just a few words to say how complex it is to do a decomposition. Is this a complex problem or not? Well, first of all, let's start from a generic decomposition. This is pretty easy, right? You have an object. You use, for example, I don't know, a cutting plane just to halve it. And if you do not have any criterion, well, cutting, it's easy. That's nothing you have to do. A little bit more complex is to compute a constrained decomposition, where after cutting, every single piece that you create has to fulfill some constraints, some requirement. This is a little bit more complex, but still very easy. And the reason because it's easy is because you can still play with the size and the number of your objects. So you have 2 degrees of freedom, which are unbounded. And if you play with them, for example, creating just tiny pieces, it's very easy. For example, if you want to decompose a very complex object into a bunch of height fields, if you create like tiny height fields just by cutting every convex vertex of your mesh with a plane, it's not complex. It's completely useless, because at the end of the day, you will get like millions of elements. But from the sake of decomposition, that's not a complex problem. Complexity comes from minimality. So if you want to compute a constrained decomposition that is minimal in the number of its parts, then it's known to be an NP hard problem. So it's very hard. And it's NP hard already in 2D. So it's a super tough problem. And the problem is that the search space that you are exploring grows exponentially with the complexity of your object, the number of elements that compose your mesh, literally. And in this framework, you have no way to find the global optimum. You just go for heuristics that try to find a good local minimum, whatever good means. This depends on the application. And it's all about picking the right heuristic. So what we're going to see in the remainder of the presentation are techniques which are heuristics to find good decompositions that are tailored for the application that we have seen. And as I said, there is a bunch of recurring approaches to solve this kind of problems in fabrication, but not only in fabrication. And if we talk about fabrication, what I can say is that all these methods, more or less, try to control these 3 aspects. They want to control the part size, They want to control the local surface orientation, and in particular, as I said, the angle that is formed by the local surface orientation and the machining direction, whether it is for depositing material or carving away material. And then they also want to control the assemblability. So once you split everything and you fabricate by parts, the ability to take all these pieces and reassemble them together to form the final shape. So these are the three major goals that are common to all these things that I've shown so far. And the techniques that are mostly used are binary space partitions. For example, taking an object, use cutting planes to halve the shape iteratively until every single piece fulfills your requirement. Graph labeling, in which essentially you solve a graph problem, for example, when you want to find the minimum cut in a graph to separate the nodes of your graph. And also mesh booleans are a quite widespread tool. So most of the algorithms that we have in the literature are based on these three techniques or combinations of these three techniques. So in this part of the presentation, we're going to see, and we're going to say something about all these three approaches. Before we go there, just a few words regarding the assemblability. First for the rigid bodies and then for flexible bodies. When you want to make sure that two or more pieces can be actually reassembled together, what you have to fulfill are both local and global requirements. And this is what makes the problem a little bit hard. From the point of view of local requirements, you want that the interface between your parts is a height field with respect to the extraction direction. So in this case, for example, you can extract this red part along this direction, whereas in this case you cannot, because these walls are preventing you to move in this direction. And this is because this portion of the interface is violating this constraint. So this interface is not an height field with respect to this direction. And this is something that can be controlled very locally, because you have to put yourself in every point of your surface and just check what is the angle between the local surface orientation and the extraction direction. Even if you are in this case, you are not sure that you will be able to complete the assemble. And the reason is that you may hit against other parts of the object that are nearby. So not only you have to satisfy this local condition, but you also have this global requirement that says that essentially there must exist a cleared extraction path. And algorithms typically look for this kind of paths, linear paths, because it's much simpler algorithmically to verify this. But in principle, you may also have more complex paths where the object can rotate and the path is not linear, maybe it's piecewise linear. The problem with this version of the global requirement is that the search space is huge, because if it's for example, if it is a piecewise linear extraction path, how many segments, it becomes very difficult to solve for this kind of paths. Also because you have to solve a collision detection problem, which is not very cheap to do. So typically you will find algorithms trying to go for this version of the global requirement. And that's everything for rigid bodies. So things that cannot compress or move in any way. If you have soft bodies, for example, silicon molds, what happens is that you can extract these pieces even if you are violating the height fieldness, because you can play with the flexibility of the material. So how do you check for assemblability in case of soft bodies? Well, the fully fledged solution will be to do some kind of FEM simulation, but it's overly expensive and complex because you have contact and friction. So it's not an easy simulation. I'm not aware of any method that is actually trying to do that in this way. What we have seen in the past is that, for example, in flex molds, the authors used projective dynamics on a thin shelf representing the mold in order to understand whether the mold could be detachable from the object. And essentially what they were doing was to measure how much the triangles representing the shell deformed through the extraction. And the idea was that the more they deform, the more difficult it is to detach the shell from the object. And in subsequent approaches, they actually moved to something that is even more simple, and it's purely geometric. For example, in Metamodes, what they play with is with the notion of height fieldness again. Essentially, they say if I'm given an extraction direction, which is represented, for example, by this red arrow, I know that all the pieces of the surface that are blue are visible with respect to that direction. So all these blue parts, I can detach them because there is nothing that is in between me and the surface. And then what they do is to propagate a distance field from these blue regions. And the idea is that the more distant you are from the blue regions, which are naturally extractable, the more difficult it becomes to extract the mold. So it's, of course, it's a proxy measure. It's not something very accurate, but it's being used and validated with very complex pieces, and it works remarkably well. So it's a good alternative, which is very cheap and easy to verify. Okay, so let's move to the first class of methods that are meant to be used for shape decomposition for fabrication. These are binary space partitions. There is lots of literature about methods that operate in this regard, and they solve any kind of problem. For example, binary space partitions to simplify objects to fulfill size requirements, to mitigate the staircase effect of 3D printing, to do the composition for packing and shipping, and there are also others. From the point of view of the methodology, we have mainly two families. We have binary space partitions that are created top-down using beam search to explore a bigger portion of the solution space. We'll say something about that. And there are also binary space partitions that are constructed bottom-up in a greedy way. So this is more or less what we have in the literature. So let's start with the bottom-up. In the bottom-up idea, typically you start with a mesh, let's say a triangle mesh or a tetrahedral mesh, and you have the leaves of your tree, which represent the different pieces of your mesh. And when you move upwards in the levels of your tree, essentially what you do is that you cluster your elements to create bigger and bigger portions of your decomposition. And so in the beginning, you take pairs of triangles and you mesh them to do sort of a quad, and then you continue until you hit the root of your tree, which again represents the whole mesh. And so if you select a level in this tree, what will happen is that it will give you a decomposition of your object into smaller pieces that fulfill your requirements. So this is bottom up. And of course, when you do this, the key component of these algorithms is how do I merge my pieces? What is the merging policy? And a good representative of these approaches is an algorithm that is called shapes in a box that is for packing. And essentially, this method operates in a volumetric discretization. So the leaves of the tree are essentially tetrahedra of a tetrahedralization of the whole object. And the merging is done greedily in order to minimize a measure that is called absolute aboxiness. What is this measure? It's essentially the volumetric difference between the volume of the oriented bounding box, the smallest oriented bounding box that contains the cluster of tetrahedra that you are grouping together, and the sum of the volumes of all these tetrahedra. Of course, the smaller this measure, the better this axis aligned bounding box is actually adhering to the surface of your cluster. And so this is repeated at every single level of the hierarchy, as I said, greedily. And eventually by selecting inner nodes in this tree, you get the decomposition that you want for packing in this case. If we go top down, the idea is that you start from the root, you have a representation of your object. It doesn't have necessarily to be a mesh in this case. There is no discretization issue like in the bottom up. And the idea is that you cut your object, you simplify into two pieces which are smaller and have different properties in terms of geometry, something that you want to achieve in your application. And then you just continue doing that until you're happy with what you have. And like for the bottom up, again, you have the problem of what is the cutting policy that I use? How do I cut? For example, I can use cutting planes. If I use cutting planes, what cutting planes I'm going to use? How many possible cuts I'm going to consider to pick the one that I want, and so on and so forth. And a good representative of this category of methods is Chopper, that was proposed in 2012, in which essentially at every single node they discretize the set of planar cuts that are considered for simplification of the object. They sample the Gauss sphere in order to have pretty much planes aligned in any possible direction. And then they consider a metric that is a composition of the number of parts that you're going to create, the possibility to insert connectors in the pieces that you create. For example, if you have something which is very thin, connectors will not be easily inserted, and so this is penalized. The fragility, the aesthetics, because you want to hide seams in least visible parts, and also the symmetry. So summing up scores according to all these criteria, they end up with finding the plane that is the best one to split into an object which is either the whole object if you're at the root, or some portion of this object. Now, let me say a few things about how these methods can explore the space of solutions, because you may have a tree which is constructed bottom up or top down, and you can still use different ways to take these decisions depending on what strategy you want to achieve. The easiest one is, of course, greedy. What does it mean? It means that every single time you have to take a decision, you take the locally best decision. For example, I'm looking for a cutting plane. I'm going to take the best cutting plane according to that score. And that's the easiest strategy that you can use. Another strategy that is a little bit more refined than greedy is what is called the beam search, and is widely used in the field of fabrication because for many methods it performs better. Here, the idea is that you want to explore a wider portion of the feasible space, and you have an assumption. The assumption is that even though your pieces in the current decomposition do not fulfill your requirements, you can still compute a ranking, so you can rank partial solutions. And if you can do that, the algorithm is actually pretty simple. You take all your partial solutions, you sort them according to how good they are, and you just continue exploring only the n best partial solutions. And this number n, which affects heavily the performance of the algorithm, is essentially what is called the beam width. So ideally, you have a solution space, which is something like this. This is not the tree representing the splitting. This is the tree representing all the possible solutions. And every single node in this tree is actually a solution. So it corresponds to a partition tree. And what you do is to, for example, in this case, the beam width is 2, which means that at every single level of this tree representing the space of solutions, you just propagate 2 nodes. And just to understand how this tree works, for example, in the case of chopper, where you use cutting planes, the number of these arcs is the number of cutting planes, candidate cutting planes that you consider. If you, for example, consider 5 different cutting planes, you will have 5 arcs, and each one will correspond to a solution. And if you go greedy, you will pick just the best one, so you propagate just one of these. If you go with beam search with n equal to 2, you propagate 2 of these. And so at every single level, since you have 5 cutting planes and 2 best partial solutions that are propagated, you get to choose among 10 candidate solutions, and among these 10, you select the best 2, and you proceed again. Among these new 10 solutions, you propagate these 2 until your partial solutions are actually solutions of your problem, until you fulfill your requirements. At that point, you will have 2 solutions, because n is 2 again, and you will just select the best one. So this is how chopper works, for example. And what is interesting is that even though beam search may seem consistently better than greedy because it considers more solutions, it is not true that it's always able to find a better solution than greedy. And in particular, what we're going to see in this presentation, in this example in particular, is that sometimes greedy performs remarkably better than beam search. For example, here is a space of solutions for a problem in which at each level you solve a binary subproblem, so you can go either left or right. And this is the space of all possible solutions, right? So we start from the root of this tree, both with greedy and beam search, and so we get to choose between 2 alternative solutions. If you go greedy, you go for the solution that is best. So you want to maximize this number. And so for greedy, you will go to C. In the case of beam search, n is equal to 2, so you don't have to choose in this case. You can pick both solutions and you continue. So in the second step, for beam search, binary problem n equals to 2, you have to choose among 4 candidate solutions. And for greedy, you have still 2 because you always move along one arc. So in this case, for greedy, you will go in G because 3 is higher than 2. And in this case, you have these 4 solutions possible and you propagate the best 2. So this one, D and E. So new level, same problem. 4 alternative solutions here, 2 alternative solutions here, and you pick the best one for greedy and the 2 best ones for beam search. And now it's interesting because the solution found in the greedy approach is actually the best one. Here you get a 9. Whereas for beam search, we found 2 relatively good solutions, but not the best one. And of course, this problem was made on purpose just to show that greedy can actually win in beam search, but this is something that may happen in practice. And it heavily depends on how you formulate the problem. If you have the right formulation, greedy may work better than beam search, even though probably statistically beam search will work better. And the other thing is that if you increase, for example, the size of your beam, and so at each level you explore, let's say, 3 alternative solutions, you can find in this example the same solution, but it's always a trade-off between the size of your N. The higher it is, the higher the number of partial solutions that you have to explore. So computationally, it is more costly, and the size of your problem, of course. Okay, so let's move to the second strategy that is most widely represented by algorithms that perform decomposition for manufacturing, and this is labeling. Labeling comes typically in 3 different flavors in manufacturing. There are methods that solve integer linear problems or Graphcats. There are methods that are completely greedy, and there are methods that are a composition of these, and they operate typically by computing first an over-segmentation of the object, a superset of your segmentation, and then they proceed by region merging in order to find a coarser decomposition that is essentially an agglomeration of the partial solutions. And in this case, typically, you will see that the over-segmentation is done greedily, and then the final step when you merge strings is done numerically, for example, with Graphcats or integer linear programming. So we're going to say something about these methods, and these are essentially a combination of the 2. Okay, Graphcats. Graphcats is a typical algorithm on graphs, very popular, that solves a multi-labeling problem on a generic graph composed by a bunch of nodes and a bunch of arcs connecting node A. And what it minimizes is energy that looks like this. So let's take a look at this energy. We have what is called the data term, which is essentially the cost of assigning a label L to some node I in your graph. And then we have a term that is called the smooth term, which is the cost of assigning 2 labels, Li, Lj, to adjacent nodes, so nodes that are connected by an arc in the graph, I and j. And what you want to find is the assignment of labels that minimizes this energy. So first of all, if the number of labels is more than 2, this problem is NP complete. So it's actually it's actually very complex. And Graphcats only finds a local minimum. And in particular, for the way it operates, its result heavily depends on how you initialize the problem and what is the processing order of the nodes. In literature, you find many methods that typically solve a Graphcat problem a bunch of times with some randomness in the processing of the nodes, and just pick the best solution to counterbalance this problem that this dependence on the initialization and the processing order. This method is heavily used in computer vision and computer graphics, and in practice, up to my experience, it works remarkably well. And just 2 examples of using Graphcats for something that has nothing to do with fabrication. Graphcat was proposed in 2004, and I don't know if it is still true, but for a long time it was the TOG paper with a higher number of citations, so it's a very popular problem. And Polycat is a paper that I published in 2013 for computing polycube segmentations, so something that has nothing to do with fabrication, but still a labeling problem. Now let's take a look at Graphcats for digital manufacturing. Ideally, so typically, when you use this tool for digital manufacturing, you operate on a graph that is the dual of your mesh, where the mesh represents the object that you want to fabricate. And so it means that if you have a surface representation, for example, a triangle mesh, your graph will have one node per triangle and one arc for each pair of adjacent triangles. And the same goes for tetrahedra. So one node for each tetrahedron and one arc for each pair of tetrahedra that are sharing a face, or for voxels, the same thing. And the labels typically represent machining or extraction directions, depending whether you are working on assemblability or, for example, CNC milling, or you're going to choose how to decompose to, for example, for 3D printing, the direction of the position of the material, and so on and so forth. So the label is something that is specifically related with the fabrication technology that you are going to use and that you want to fulfill its requirements. So this is the energy again, and typically in a formulation for digital manufacturing, you will have a data term that looks like this. You get some number, Fi of L, so a function of the label if the problem is feasible, or you get infinite otherwise. Let's make a practical example. Let's say that we're going to compute a decomposition for CNC milling. If you want to machine this part with a milling machine, this cost is going to be infinite, because we know that we cannot, because there is an overhang. So this is a typical case in which you will get an infinite cost. So this, the label representing this machining direction cannot be associated to this portion of the surface because of this overhang. So that's an infinite cost. So it's a label that you will never see here. On the other hand, if you have this label associated with this machining direction, this portion of the surface can take the label, and so you will have here something that depends essentially on the angle between the surface here and this machining direction. So that's typical. That's the typical data term when you solve decomposition for manufacturing with Graphcats. And then in the smooth term, you just take care of literally the smoothness of the interfaces. You want to promote as smooth as possible interfaces. And another role of the smooth term is to avoid that you have like lots of tiny islands. Since you pay for having boundaries between different regions, intrinsically, when you minimize this energy, you do not have islands, but you have like bigger pieces that are the pieces that you want to have, for example, for fabrication. And this is used in a variety of different methods. For example, in surface to volume is used on a tetrahedral mesh, and labels represent the extraction directions. In height field, the composition is done on a triangle mesh, and the labels represent the height field directions or the milling directions if you want. In 4-axis milling, the same thing. In rigid molding, the method works again on volumes, and the labels represent the molding direction, and also for the double height fieldness. So all these methods deal with different fabrication technologies, solve different problems, but if you were to implement them, you would have to essentially implement pretty much the same algorithm. What changes is the meaning that you associate to the labels, and of course there is a lot of pre and post processing that may be different, but the core of the algorithm is the same and is essentially a Graphcat formulation. Okay, let's go to greedy labeling. Greedy labeling does not typically work as well as Graphcats, but when you have the right idea, it becomes extremely powerful. I'm just going to propose you an example of this. An algorithm that I just loved because of its simplicity and is completely greedy. This is this paper from Ziqi et al. In SIGGRAPH 2019, which is called volume-aware molding, if I remember correctly. And essentially here, what you want to do is to associate labels to a tetrahedralization of the space surrounding your object that represent essentially the shape of the molds that you're going to use to fabricate this object. And the method works greedily, essentially by, first of all, computing a bipartition, so a decomposition into two pieces of the hull, enclosing this volume that contains your object. Essentially, for two candidate molding directions, the portions of the surface are just grown such that you have just two pieces covering the whole hull. And then these labels are propagated inside the volume in order to define the cuts between the two modes. And this is done, sorry, okay. And And this is done with an extremely simple yet effective idea. You take any pair of adjacent points in your tetrahedral mesh, and you just compute the shortest path from those points to the surface of the outer hull. And if you end up in two different semi-hulls, so if you end up in two parts of the hull with different label, you know that there is going to be a cut separating those two vertices. And that's it. And this computes a separation between one mold and the other that then you will combine to compute your shape. And then there is another type of cut, which is a cut within the surface of the same mold, which is necessary, for example, when you have homogeneous surfaces. And the idea is, again, very similar to the previous one and as simple as that one. You take, again, two pair of vertices which are adjacent to one another in your tetrahedral mesh. You compute the shortest path. In this case, you see, for example, that they end up on the surface with the same label. And what you do is to compute this kind of surface that is bounded by these shortest paths. And if there is an intersection between this surface and your object, you know that you have to have a cut here in order to allow the mold to open itself and to be extracted without heating, for example, in this portion of the chair. And here you can see the blue cuts, which are the ones of this kind. So essentially the cuts that separate the two molds, and the red cuts, which are cuts of this kind, which are cuts that are essentially necessary to cope with heterogeneous objects or very complex geometric entities. And that's it. So super simple idea, super effective. And here is an example of an object, extremely complex object can be created with molding with this technology. And if you take a look at the geometry that is created with this greedy approach, is extremely complex. So this method is extremely powerful. And what I like a lot about this method is not only the method in itself, which is easy, but it's also the journey that took the authors to start from 2016 with a method that was called flex molds. And then in 2019, they had another method, Metamodes, and eventually they came up with this idea. And if you take a look, so this is like the time unroll of their works on molding. Of course, in terms of results, the latest work is the one that is superior to the previous one, because otherwise we wouldn't be talking about SIGGRAPH papers in the first place. But the most interesting thing is that if you take a look at the complexity of these approaches, actually this one was the most complex of them all. It was involved with the computation of a coarse quad layouts, and then the parts of these layouts were used as seam parts to cut the mold, etc. And then they had this paper in 2018 where essentially they solve an integer linear problem to find this decomposition or this labeling. And only in 2019, they were able to simplify the idea such that with a very easy to implement greedy strategy, they were able to compute something which is much more powerful than this and this. And so to me, this is just an example of simplicity as being complexity resolved, and it's something that I love because it really shows that to be simple and effective, it takes a lot of time and experience. It's not something that comes for free. Okay, so final, just a few words regarding the final strategy used for decomposition for manufacturing, and this is mesh booleans. Mesh booleans comes pretty much in two different flavors. So one way of using them is through extrusion. For example, in this case, you know what are the colors associated to the surface of this object, and you also have a volumetric representation of this object. And by extruding these surface patches along an extraction direction, which is this, you get pieces, solid pieces that can be fabricated. And this is done through Boolean operations with respect to a volumetric discretization of the input object. And this is the same object after being printed and reassembled. So that's a way of using surface Booleans for defining from surface patches volumetric entities that can be fabricated. And the other typical approach, and the other typical approach of mesh Booleans to surface decomposition, of shape decomposition, is through intersection. Here, for example, we have an object which is not an height field, and the goal is to decompose this object into height fields such that the object can be printed, can be fabricated with CNC milling machines with 3 axes in a single pass, as you can see here. And the idea is to define the smallest number of axis-aligned bounding boxes that detach a portion of the object that is a height field. So it's a Boolean operation between all these boxes and your object. And progressively, they detach from what remains of the object another portion that is an height field. And when you conquer the whole volume of the input object, you have a decomposition that is suitable for this type of manufacturing. One thing that we have to remember, and it's very important when we talk about mesh booleans for manufacturing, but in general mesh booleans for any kind of geometry processing intent, is that mesh booleans essentially require, the hard part of mesh booleans is finding the intersection between mesh elements. And this computation is not at all robust on floating point machines like our computers, because the number of numbers that we have in our machines is finite, and intersection can arise at any point, and this point may not be representable in our machine. And the effect of this is that essentially when we look for intersection between, for example, these two segments, which amounts to saying whereas C and D stay at opposite sides of A and B and vice versa, this type of check on floating point is completely unreliable. And it means that you will find intersections that are not there, you will not find intersections that are there, and this inconsistency can break your algorithm in very different ways. So there are methods to obtain like a neat check like this, but these methods are based, for example, on rational numbers, exact predicates, and are robust but overly slow. You have to take into account 1 or 2 orders of magnitude slower than floating point implementations. And so this is just to say that when you design an algorithm for decomposition through mesh booleans, you have to remember that you're going to pay this cost if you want to be robust. And I mean, using booleans can still be the right choice, but you have to be aware of this slowdown. On the other hand, if you use approaches, for example, labeling with the interface smoothing just to detach the geometry of the interface from the discretization of your mesh, all these things are float friendly because they do not involve inserting new points at the intersection between mesh elements, which is really the complex part of mesh booleans. And another important thing, this is the last one before we conclude, is that many times algorithms that strive to decompose an object to fulfill requirements of tight requirements of manufacturing, for example, height fieldness for 3-axis Cnc milling, if they were used directly on complex shapes like this statue, they would produce an overly big number of pieces just because of the tiny details that you may have in your object. So in reality, pipelines operate in this way in which, given the input shape, they apply a sort of defeaturing that can literally be something as simple as a Laplacian smoothing, such that you simplify the geometry and then you do the decomposition on this simplified geometry because you are able to essentially maintain a lower number of elements in your decomposition. And once you have this decomposition, you just restore back the details in order to come back to be as much as possible close to the input requirement. And so in terms of algorithms, typically this amounts to storing, for example, the differential coordinates of your points in the mesh that represent the local surface orientation of the mesh and essentially the local behavior of the mesh around the vertex. Then you apply the smoothing, and so this type of information is lost. You do the decomposition, and then you solve a problem in which in the new mesh decomposed, you want the differential coordinates of your mesh to be as close as possible in the least square sense, as you can see, with respect to these differential coordinates, which represent the real features of the input shape, subject to fabrication constraints. For example, this means without violating the height fieldness if your decomposition was for 3-axis Cnc machining. Okay, and this was all for this part of the tutorial. So just a few words to conclude, and then we're going to move to the question and answer time. I just want to remark that shape decomposition for fabrication comes in many different flavors and is useful for a variety of different things, machining hardware and technology and so forth. I think it's clear by now that it all boils down to control two basic ingredients. The local surface orientation is a big part of decomposition algorithms, and the other one is part size that can be intended as static, for example, to fit the extents of a machining hardware, or dynamic, for example, for assemblability, where you know that a part is moving and you don't want to collide with other parts of your object. So you still need to cope with the size. And this is always a hard problem. We've seen that this MP complete, so it's very hard, but we have good heuristics to solve. And I'd like to remark that greedy is not a bad word, and we have wonderful algorithms that are greedy and are extremely powerful for decomposition for manufacturing. Ideally, in my opinion, when the idea is good, greedy algorithms are faster, for example, the beam search, easier to code, and are extremely powerful. So that's a message that I would like to deliver. And with this is everything, and I thank you for the attention, and let's go for the question time. Thank you.
So do you have any questions for all the presentation? Yeah. So I'm here, but the other two presenters are currently remoted, but they will respond also the question. I can just say to them and they will answer.
Thanks for the tutorial. I had a question about the second part of the tutorial. So you talked about how it's possible to optimize the shape and the position of elements to stand under gravity. Have you considered also other types of loads, like for example in the architectural context? It might be interesting to look at how a structure performs under wind conditions or like snow under the roof and stuff like that.
Yeah, thank you for the question. Yes, so sure. Most of my presentation is about the gravitational stabilities, but if you see, we have the lateral stabilities, which is exactly the things you said for the wind. And for extra loads, you can do this. So you just have just change the gravity to the loads you want, and it will be the same. Or if you have several setups, like I just not just want the gravity to be my main force, but also have wind and other loads, you can have to use 3 different infeasibilities. Each one have the force you want, and sum them. You want them to be 0 at the same times. Then you can have like stability for multiple loading cases. So that can be done, yes. Thank you.
Thank you for the talk. I have a question about the third part, about the shape decomposition. So in the talk, there were a lot of problems, solutions describing single optimization shape decomposition algorithms, where you essentially give a single output, a single shape decomposition. But in case that of a multi-objective optimization problem, where you would have like, let's say, several conflicting criteria, do you know of any existing work which basically computes multiple shape decompositions at once, and then let's, for example, let the user choose within a given, like let's the user choose between a variety of different shape decompositions?
It's like Pareto front things, right?
Yeah, something like that, exactly.
Marco, could you hear us, or could you answer the question?
Yeah, I could hear. I don't know if you can hear me.
Yes.
Oh, okay. So, hi, everybody. So there is a bunch of methods that compute a single shape decomposition considering multiple factors. For the context of fabrication, there is no method that comes to my mind that does what you just said. So computing like a bunch of alternative solutions and let the user pick the favorite one. So I don't recall any particular method that does this, but this may actually be pretty useful because there is a lot of subjectivity in the topic, so it may be very useful actually.
Yeah, I just imagine it being a hard problem because you also have the discrete component of the number of pieces, for example, which comes into play. Yeah. right?
Yeah, absolutely.
Yeah. Thank you.
You're welcome.
Oh, okay. Thank you for the talk. Very good one. I just have a question regarding the second part. You mentioned about a lot of things about like assemblability and the stability, like in this kind of static assembly structure. Is there some work about how to consider the functionality, like intentional motion in the assembly structure?
Probably yes. Sorry. Yeah, yeah, it's a good question, but yeah, I haven't go into this direction, so maybe I'm not the good person to answer. Maybe Peng have some ideas about this, like you mean like kinematics stability, like you have objects can move around and you want,
exactly.
Peng maybe have some ideas about this.
Okay. Hi, Desmond. So when you talk about intentional motion, do you mean you want the structure to move? I mean, they transfer some motion, right?
Yes, exactly.
Okay. So I think this. Okay. So I think that is I mean, this kind of assemblies is beyond the scope of this tutorial. So in our tutorial, actually, we are focusing on structures. That means the degree of freedom is 0. So when you talk about the assembly can have some intentional motion to transfer the motion, is actually the mechanisms. So there is another classes of works on mechanisms. I think, yeah, so indeed, there are actually quite a lot of this kind of works. So for example, they can combine gears or linkages or 3D cams, this kind of mechanical parts to transfer the motion. Yeah, but that's beyond the scope of this this tutorial.
Okay, thank you for your answer.
Yeah. Okay, thank you for the question.
Sorry, maybe I have a last question or a question for you as well about the stability analysis. So your work focused mainly only on rigid pieces.
Yeah.
Would you maybe in the future, or do you know of any work that consider flexible pieces that could have some elastic deformation maybe in a certain range? And what would be the locking possibilities or stability possibilities?
Thank you for the question. Yes, I see papers from NYU have solved this, not completely solved, but solved this kind of elasticity contact problems. It's actually a problem that originated in mechanical engineering. They simulate this contact FEM, like you have gears or any like fixtures, and you have external loads, and how this fixture or the gears like transmit the force and without breaking itself. And this kind of problem already been researched for a while. And there isn't a paper about this in talks to optimize the contact shape to make the stress minimum, but also, yeah. And I think for this kind of problem, there's still more to do, especially you have very complex assemblies. So the both stress inside the structure, you have to reduce. Also, you want to make sure the assembly is stable. If it's rigid, right, you cannot let it falling down. So have both constraint considered, and if you have like 100 or 20, 200 parts assembly, it's a pretty challenging problem. You have to optimize a lot of contacts, and that's probably a good direction to look forward. Yeah, and also friction, and also friction, like elasticity is one problem, and friction is another problem. If you consider both, that's also very hard. Yeah.
Okay, thank you.
Oh, by the way, I see some people also talking about snap joints. Like you can click some parts into the structure, and there's a paper I just showed that uses a snap joint to create a shell structure. So you don't need to print the whole volumes, you just print a shell. But because the shell is very weak in terms of the contact, you cannot connect the two shell structure perfectly if you don't use glue. What they do is they use this kind of clipper joints to connect them so that even you have very small contact areas, you still can make the structure stable. So yeah, that's also very good research. Yes, thanks.
Thanks. Okay, so I guess if there are no further questions, we can thank the speakers again and go to lunch.
Thank you for attending this tutorial. Thanks.
Thank you for joining the session.
Thanks to everybody for showing up.